Welcome to the Explainer. Today, we're going to dive into some of the tiny little components that keep our increasingly complex cars running and, more importantly, running safely. We're going to break down exactly how engineers make sure that every single piece of data gets exactly where it needs to go flawlessly.
So let's start with this idea. You got to think of a modern car less like a machine and more like a high-speed computer network on wheels. It is constantly sending huge amounts of data between all its different systems. And this isn't just for your music, it's the car's actual nervous system. All right, so how does this whole thing work?
Okay, so to really get the challenge here, we first have to understand the different data highways, the communication networks that are buzzing around inside a vehicle. And believe me, they have evolved a lot.
All right, first up we have CAN. This is the old reliable, the workhorse. For decades, it's been the go-to for all the basic stuff, like telling your mirrors to adjust or checking the engine temp. It's not fast, but man, is it stable. The best way to think about it is like different parts of your car sending simple, super reliable text messages to each other. Now, when things get serious, when safety's on the line, cars switch over to FlexRay. At 10 megabits per second, it's faster and way more robust, which makes it perfect for the really critical systems like your anti-lock brakes or active suspension. So if CAN is like a simple text, think of FlexRay as that high-priority group chat where you know every single message has to get through, like right now.
And of course, you can't forget this sound system, right? Well, that gets its own special network called A2B. It's pretty quick, running at 50 megabits per second, and its only job is to make sure everything from your music to your phone calls, even your car's noise-canceling system, has its own clean highway for perfect audio.
But the real game changer, the thing that makes all the new tech possible, is automotive Ethernet. This is the data superhighway. We're talking speeds that go from a solid 10 megabits all the way up to a mind-blowing 10 gigabits per second. I mean, that is thousands of times faster, and it's absolutely essential for handling the massive flood of data from cameras, radar, and all the sensors that self-driving features depend on.
So, what's the big takeaway here? The demand for speed has just exploded. We've gone from sending the equivalent of simple text messages for basic controls to streaming multiple high-def video feeds all in real time. And that huge leap in speed, well, that brings a whole new set of problems to the table. Okay, so with all this speed comes a big problem: electrical noise. All of these high-frequency signals zipping around the car can actually interfere with each other and corrupt the data. So how in the world do you protect the really important data from all that chatter? Well, the hero of our story is a tiny little component called a common mode filter, or CMF. Its job sounds simple, but trust me, it's incredibly hard to pull off. It's basically a gatekeeper for the signal. And this slide just lays it out perfectly. The CMF has to manage two very different signals. On one side, you've got what's called differential mode. That's the good stuff, the clean, structured data we want to keep. And on the other side, common mode. That's all the junk, the random electrical noise that the filter has to find and destroy. Look, building a filter for that old, slow CAN network, it's pretty straightforward. But for the Ethernet superhighway, whoa, that is a completely different ballgame. It's got to pass a way tougher inspection.
So what's the big deal? Why is it so different? Well, Ethernet is just insanely faster and way more sensitive to noise. The accuracy it needs is just extremely strict. It all comes down to this. A standard filter gets a 3-point check, but an automotive Ethernet filter, it has to pass a super tough 5-point inspection using something called S parameters. These are basically a series of tests that measure exactly how a signal behaves as it goes through the filter. All right, test number 1, insertion loss. This basically asks a really simple question. Does our good signal actually get through? We want the filter to be totally invisible to the data, because if you lose too much signal here, it's like someone's whispering a critical command. The car's systems might just miss it.
Okay, so test number 2, common mode rejection, is the flip side of that coin. This one asks, how good are you at blocking all that nasty noise? If a filter fails this test, it means all that static and interference is leaking into the data line, and that could corrupt really important information.
Now this third test, mode conversion, this one is so important for these high-speed networks. It's looking for something really sneaky. Is the filter itself accidentally taking the good signal and twisting it, turning it into noise? That's a huge problem. So for this test, the lower the number, the better. Okay, test number 4, differential return loss. Now we're getting into tests that are specifically for Ethernet. This one is all about reflections. We need that data signal to just flow forward smoothly, not hit the filter and bounce back like an echo. A great filter has almost no reflections, so again, a lower number is what you're looking for.
And finally, the last Ethernet test, SCAD11. This one is like a detective with a magnifying glass, hunting for noise created by the tiniest microscopic flaws in how the filter was built. Even the smallest physical imbalance can create noise, so this test makes sure the manufacturing is incredibly precise. And you guessed it, the goal is the lowest number possible.
Okay, so we know the 5 brutal tests it has to pass. The big question is, how do engineers actually build one of these things to pass with flying colors? Well, it's not magic. It really comes down to balancing 3 key things with insane precision.
First thing you need is high common mode inductance. Just think of this as the filter's brute strength. It's raw noise-blocking muscle. The higher the inductance, the more power it has to just crush that unwanted noise. That's what helps it ace those SCAD21 and SCAD11 tests.
Second, and this is absolutely crucial for high-speed signals, you need super low parasitic capacitance. You can picture this like a tiny, unwanted leak in the data pipe. At high speeds, that leak can just sap the energy right out of the signal. So by keeping that capacitance as low as possible, you keep the pipe sealed, letting the data blast through perfectly.
And last, but honestly, this might be the most important piece of the puzzle for Ethernet, is perfect winding symmetry. You see, inside the filter are these tiny, wound-up coils of wire. If there's any microscopic difference in how they're wound, the length, the shape, the spacing, it can cause all sorts of problems, creating reflections and turning good signal into noise. Getting that symmetry perfect is what separates a good CMF from a great one.
All right, so we've waded through a lot of technical stuff here. Inductance, capacitance, S parameters. What does it all boil down to? What's the real mission of this tiny little component?
It really is as simple as this. A great common mode filter is an invisible guardian. I mean, that's its whole job, to make sure that every single piece of data, from the camera that sees a person crossing the street to the radar that sees a car braking up ahead, gets where it's going cleanly and instantly, every single time.
And that really leaves us with one final, pretty heavy thought. Think about it. As we hand over more and more control to our cars, asking them to make split-second life-or-death decisions, the purity of every single one of those signals is everything. These tiny, unseen components proven through these incredibly tough tests are really the fundamental guardians of our automotive future.